Jack's corn.
Get your stupid ass moving. This fool.
You in trouble now, fool! Come on, damn it! You ain't even gonna touch me, bitch. Come on.
If Leo ran me one more time. Big Sis is gonna put a hurting on you now.
Union Station in New Haven. This is train 1, this is train 2. No, you get into this train and all the blinds are drawn. You cannot look outside. There's a reason for that. It's not because it's going through certain parts of New Jersey. It's because we're going to do a scientific experiment that requires you not to look outside. So here's, let's say you're on this train, there's another train. Before they shut the blinds, you can look out and see the other train. You can see it's also standing there. Then they close the blinds and you settle down and you, okay. So the question is, will you know? And what Galileo noticed is that you cannot tell. You cannot tell in a moving train that it's moving as long as it's moving at a constant velocity. That's very important. If it's picking up speed and slowing down and so on, you will know. But if it's going at constant velocity, nothing will betray that motion to you. That's a principle we have all experienced. Once in a while when the thing is very smooth or a plane is going very smoothly, you yourself realize that you're not aware of that motion. So the principle of relativity is a statement that you cannot tell when you're inside a train whether it's at quite a constant velocity or not. So where is the relative in all of this? I'm going to come to that. So if you open the blind now and you look at the other train, suppose you find the other train is going like that at 60 miles an hour. Will you know whether you're the one who is in motion or the other train? Now, this has happened to us quite often when you're parked on a slope or you put your brakes and the car is in a slope, you see the other car going forward, you think you're slipping, you press the brake harder, you get the impression of movement. So the whole thing is, if you look out and you see this train going that way, can you tell? The answer is, you can tell there is motion between the two of you. That is a fact. So velocity between two such people is relative in the sense that we can perceive it, but we cannot be sure who is actually moving, or whether there's any real sense in which one of us really is moving. In fact, if these two trains were in outer space, we just wouldn't know. Now, if you look at the other side, let's say, you open the window here and look, you see a lot of cows and streets. Cows are running at 60 miles an hour. Okay. Now the question is, what do you think is happening? Is it the cows or is it the train? So I know what you're going to say. You're going to say it's got to be the cows, but you realize theoretically Amtrak trains can move. So that's a possibility. You're not willing to admit that even though it's very remote. So you keep thinking it's the cows, but it could be. It could be possible that the cows are not moving, it's the train. So once again, there is no way to resolve the difference. So the summary of what is mentioned here is that constant velocity doesn't do anything that you can measure. If you're inside, you cannot figure out that's being given to you. But that's not true for non-uniform motion. That's not true for accelerated motion. For example, if the engine driver slams the brake, you're going to ram into the seat in front of you. Now if the blinds fly open and you look at the other train, it'll be decelerating the opposite direction. Can you say, nothing is happening to me, you're the one who's accelerating the other way? Well, you cannot say that. First of all, you've lost all your teeth. You cannot say anything. So, can you scribble a note and say, I'm not moving, you're moving? Well, he'll say, if that's the case, how come you have no teeth? Because accelerated motion, namely the slamming of the brake, produces effects that you feel. You cannot pass the buck to the other person and say you're moving the opposite way. Or if you're an astronaut and your rocket is taking off, you're the one who feels all the G-forces. You cannot argue that the rest of the planet is going the opposite way because they seem to be doing fine. So here is the main thing. If you're inside a closed train and the train accelerates or decelerates or goes on a curve, you can tell. If it's going at constant velocity, you really cannot tell. That's it. That's what Galileo said. That's called Galileo's principle of relativity, and it's more than 300 years old. So then the next person who comes in, not much later, is Newton. So what did Newton do? Well, Newton actually not only agreed with what Galileo said, he actually explained why it is true. So I'm going to tell you how, in Newton's point of view, you can actually understand what we all are aware of. Well, Newton, as you know, wrote down 3 laws of physics. I'm going to only talk about the first law. The second law says something is equal to something else. But I'm told in alumni reunions, I should not write any equations. that every equation costs the development office $600,000. So, no equations. So I'll just take the first law. Okay? The first law is a rambling sentence, so it's quite safe. It says the following. It's the law of inertia. According to the law of inertia, if there are no forces acting on a body, it will either stay at rest, if it started at rest, or if it had an initial velocity, it will keep maintaining the initial velocity, unless it's acted upon by a force. That's the first law. Basically, the first law says the velocity of an object will not change unless a force acts on it. Now, we're all familiar with the first law. I mean, here it is. I take this cup here, I put it there. No force is acting on it. It stays where it is.